Okay, hello everyone. It's working. All right, so let's start with the old P. So a few years ago, this is what the class P looked like. It was this mess of really important and nice, mathematically nice problems for which some people showed some algorithms and got stuck on these algorithms for many years, and they tried, they gave up, they moved on to other problems, and so on. And we had no we didn't know any connections between these problems. We didn't know any structure inside the class P. And then we started seeing these reductions. So just want to say one way to look at this, the old P, is that we had all these conjectures. Each one of these was a conjecture of its own. The conjecture that the current algorithms are optimal. But then we started doing these reductions, and and with fewer conjectures, we actually so because of these reductions from threesome to these other problems, now you don't even need the conjectures about the other problems. You can just assume that threesome cannot be solved faster. Then you immediately get that these other ones cannot be solved faster. And then you can move on to other problems if you want. So we've seen many examples of threesome lower bounds today. In the rest of the workshop, you'll see many examples of strong ETH lower bounds that you get if you assume that C and F stat cannot be solved faster. There's also the APSP lower bounds, also all pair shortest paths. What's special about these is that most of the problems in the class are actually equivalent. So if you solve one of them faster, you get faster algorithms for all of them. Whereas for the others, other classes, solving them a problem in the class faster only implies that the corresponding conjecture is false. And I think this is a very nice picture that we're starting to get. We're starting to understand the class P. But of course, there are many more things to do. There are many problems that we still don't have kind of nice lower bounds for. And what I want to do in this talk is just to tell you about a little bit about some of the recent progress that we've been making. The first part of the talk is going to be a conservative one. I'm going to tell you about some works where we try to strengthen the foundation. So the understanding that we're gaining for P is because of these conjectures. And these works that I'll tell you about try to get better conjectures that are safer, that are less likely to be false. And you'll see that while doing this conservative work, we're actually discovering some new phenomena that I'll tell you about. In particular, this very exciting recent work where we show that even shaving log factors can be hard for some problems, which I'll tell you a lot about on Wednesday. And then in the second part of the talk, we'll be more liberal, and we're actually I'm gonna tell you about a new conjecture that we make that allows us to explain many other important problems. And then, if we have time, the last part, I'm going to tell you about some approaches for bypassing the lower bounds. Okay, so let's start. So why do we need better conjectures? Well, because these conjectures, we find them plausible, but we don't really have any amazing consequences that would happen if they turned out to be false. So if we solve threesome faster, then what would happen? We don't really have many results that show surprising consequences of these conjectures being false. So one way to get a better foundation would be to get more of these results. But what we do is something a bit different. We just try to replace these conjectures with better ones. And in this paper with Virginia and Huacheng, we look at this new conjecture, which takes these three popular conjectures and assumes that at least one of them is true. So to refute our new conjecture, you have to refute all three of them. So you have to solve all three of SAT, threesome, and all pair shortest paths faster. And the main result in our work was that there are actually nice, simple problems that have tight lower bounds under this new conjecture. So there are some problems you can solve in n-cube time. And if you solve them faster than that, you refute the three conjectures. And these problems are so simple that you can then reduce them to other important problems. So let me show you one example of one of these problems. So it's a very hard n-cube problem. It's a problem about triangles in a graph. The input is a graph in which every node has a color. And you're also given some integer delta. And the question is, so I ask you, is there a triple of colors that have at least delta triangles in them? What does it mean? So when you look at a triple of colors, like blue, green, red, you see some number of triangles. So here in this picture, you see 2 triangles. And just the question is there some triple that will show you at least delta triangles? So are there like delta triangles with the same kind of colors, matching colors? A trivial algorithm solves this problem in n-cubed time. Just going over all triples of nodes gives you n-cubed. And what we show is that if you solve the problem in n to the 2.99 time, then all 3 conjectures would be false. And to get a bit of intuition about this problem, notice that when delta is 1, if I always ask you with the question when delta is 1, then I'm just asking you if there's any triangle in the graph. I'm just asking, is there a triple with some triangle? And then you can solve it faster with matrix multiplication in subcubic time. So it's natural to ask, so what happens when delta is 2? We thought about this, and we came up with algorithms that solve it in truly subcubic time for any constant delta. And then notice that our lower bounds are also super quadratic for any constant delta, more than 6. And what this means is that we get this hierarchy of problems with complexity between n squared and n cubed. So the question of 10 matching triangles has some complexity in some interval, like say around n to the 2.1. But then the 100 matching triangles problem has complexity in a later interval between n squared and n cubed. So I think this is a nice phenomena that we noticed while working on this project. Okay, so that was the first work that I want to tell you about. The second one, I'm just going to go over it quickly because I'm going to talk about it for 45 minutes on Wednesday. So in this work, we look at the strong ETH and the strong ETH lower bounds. So in recent years, we're seeing so many of these strong ETH lower bounds that are really great. They're from all over computer science. A recent example is from economics for a succinct stable matching problem. And what we do in this work is that we look at this class and we find a subclass of it, some of its coolest problems, like edit distance and LCS, and we show that they are actually harder than what you thought. And so what do I mean by that? So we look at SAT, and then SAT in its general form gives you, you're given some function, and you're asked if the function is satisfiable. Now, depending on the representation of this function, and depending on how complex this representation is, it's going to be harder or easier for you. If I give you, simple things like DNFs or CNFs, it should be easier to figure out if this thing I gave you is satisfiable than when I give you, a complex circuit like a polylog depth circuit or a complicated Turing machine. And what the strong ETH says is that even when I give you a CNF, you cannot solve SAT in 2 minus epsilon to the n time. Notice that this is kind of the lowest place where you can put the bar. Below it, we do have faster than 2 to the n algorithms. In particular, for CNF SAT, there is 2 to the n over n to the 1000 algorithms. And so the higher up you go in this hierarchy, the more believable strong ETH becomes. So if you assume that NC circuits, polylog depth circuits, you cannot solve SAT for them faster than 2 to the n, then this is a safer assumption. And when you go high enough, we don't even know anything better than 2 to the n. And so the main question that we ask is whether we can replace strong ETH with C strong ETH for a rich class C. And it wasn't clear from previous work because all the reductions really used that CNFs are simple. And our main result was that we go very high in this hierarchy. We show lower bounds under the branching program strong ETH. It doesn't matter for now what it is, but the point is we can say things now that are like, if LCS or edit distance can be solved in truly subquadratic time, then SAT on really complex things like arbitrary circuits of Lilov and depth or very large Boolean formulas can be solved faster than 2 to the n. And a very cool kind of statement that we make, that we can get because of this new reduction that we show, is that even these mildly subquadratic runtimes, even n squared over log to some power n, will have big consequences. It will imply new SAT algorithms, and which will in turn imply new circuit lower bounds. So this might be difficult. And just remember that for these problems, there are like log squared shavings. And now, now it's really interesting to get this log to the 1000 down to log the 2.1. And, I'm not going to promise anything, but maybe on Wednesday I will show you how to do that. Okay, so that was the first part, the conservative part. And now let's try to classify more. Let's be more liberal now, and allow ourselves more. So there are still fundamental problems for which we don't have lower bounds, like max flow and maximum matching. And I hope that by the next Simon's workshop on this stuff, we will have answers for these problems. A really cool result of the group from San Diego shows that there might be some barrier for showing strong ETH lower bounds for these problems and many others. And what this sort of says is that we might have to use new conjectures in general. I mean, one might have optimistically hoped that one conjecture would explain all of P. It's sort of like in NP, one kind of conjecture explains everything. But the recent progress is showing that P might be more interesting than that, and different problems might be actually hard for different reasons, and we might have to use more conjectures. So with that in mind, I hope you let me introduce this new conjecture from our paper with Arthurs and Virginia. And this conjecture is going to allow us to give a really cool lower bound for a very fundamental problem for parsing. So the conjecture is going to be about K-Clique. So give you a graph, ask you are there K nodes that form a clique. You can do it trivially in n to the K time. You can use matrix multiplication and get n to the omega K over 3. Combinatorially, the best thing that's known is only log factors better than n to the K. And what we show is that if you assume that these algorithms are optimal, if you cannot improve them, either this one or that one combinatorially, then you get some cool lower bounds. And so the parsing problem that we get a lower bound for, to define it, I need to remind you about some definitions from undergrad. So a context-free grammar is something that looks like this. It's defined over some alphabet, and it defines a language by you start from the start symbol, you apply some arbitrary sequence of derivation rules until you get some word, and then this word is in the language of the grammar. Okay, so these languages, they have a ton of applications. They represent many things, and so they're really useful because they're the most expressive languages that computers can parse well. And the computational problem that that we're interested in is I give you a grammar and I give you a string and I ask you can you get the string from the grammar. So say the grammar is of constant size and the string of length is of length n. How fast can you decide if it belongs to the grammar? And the more kind of standard parsing problem, you also need to tell me how you get it from the grammar. What's the derivation? And so, a very important question is what is the time complexity of this problem? And, many people have tried to get better algorithms. There's a ton of parsers. All of them all of these ones, they take cubic time. And on general grammars, when the grammar has certain properties, these things can be better or worse. A classical parser from the 60s is some kind of dynamic programming, and it gets n cubed. It's very simple. And a breakthrough by Leslie Valiant from 75 showed that you can kind of do this dynamic programming with fast matrix multiplication, with Boolean matrix multiplication, and you can actually get this runtime for parsing when you use matrix multiplication, and when you don't, you can shave logs with a combinatorial Boolean matrix multiplication algorithm. And this was a very nice algorithm. And, well, it's never used in practice because matrix multiplication is slow. And so this leads to two important questions. The first one is, can we, first of all, theoretically, allow yourself matrix multiplication? Can you do better than Valiant's parser? And the other question is whether you can combinatorially beat n cube time. And what we show is that if you want to believe this K-Clique conjecture, if you want to assume that you cannot do better, there's no better algorithm for K-Clique, then the answer is no to both of these questions. Besides parsing, we found out 2 other problems that are in this class. Two problems that have very good lower bounds under this K-Clique conjecture. One of them is RNA folding from biology. So you should pay attention to this class. You know, if the problem you're working on might have a lower bound from K-Clique. Okay. All right. So the last part of the talk is going to talk about how you might try to bypass a lower bound. So when you have I tell you there's your problem has a lower bound, then you should ask more questions, right? The first thing you should ask is, well, can I do a better, can I get a faster algorithm when I allow approximation? And we do have some kind of simple results that hardness approximation results in P that follow from the reductions. But for many kind of really interesting questions, we don't. And I feel like we need some new tool here. And my favorite example is edit distance. So it's known that you can do a polylog approximation in near linear time. But it's not known, I mean, the question is, can you get like a constant factor approximation in truly subquadratic time? So this, besides approximation, the second way you can try to bypass a lower bound is by restricting the class of inputs. So an interesting open question is, can you solve diameter in truly subquadratic time on planar graphs? It's known that on general graphs you cannot under strong ETH. And these questions of restricting inputs, they are nicely studied under the parameterized complexity framework. So there you look at some other parameter besides the size of the input, some parameter k, and then you ask what is the complexity in terms of both k and n. And kind of it's been studied a lot for NP-hard problems, but in 2 recent papers, it's proposed to study it even in P. And in our paper, so Josh is going to talk about this paper more on Thursday. Just to give you one kind of cool statement that we get. So we show that the diameter in sparse graphs, in which the tree width is k, you can get an upper bound that is kind of f of k times near linear in n. Remember, you cannot do a subquadratic. And this dependence on k is 2 to the O of k log k. And then we show that this dependence cannot be improved by much. So 2 to the little O of k would refute strong ETH. Another example along these lines of, from a different paper with Arthurs and Thomas and Virginia and Orr. We look at the subtree isomorphism problem. Very, very basic question. You're given 2 trees, H and G, binary trees, and you're asked if one is contained in the other. And so you're allowed to like swap children and so on, but you need to get H to be in G. Okay, the first thing we showed was that there's a quadratic lower bound for this under strong ETH, and a matching upper bound has been known since the 60s. But then we looked at restricted cases where the depth is at most H. And then, so there's a simple 4 to the H algorithm, and we got this 4 down to 2.85. And then we noticed that our lower bound gives 2 minus epsilon to the H. This 2.85 will not be 1.9 under strong ETH. Thanks.
We have time for questions.
How do you formalize combinatorially in that?
So the reductions themselves are combinatorial. So for us, it's always been like it doesn't use matrix multiplication. It doesn't use fast matrix multiplication. There's not a good formalization for it. But basically, I mean, any formalization that would make sense is going to transfer from our reductions, is what we mean by our lower bounds.
There are 4 of this analytical conjecture. Are there any other candidates that are, would make sense to consider? as a natural conjecture for proving hardness or something?
So Josh is also going to talk about the hitting set conjecture, which is essentially a variant of strong ETH, where you change the quantifiers. And again, the work of the San Diego group shows that this conjecture might be necessary because there's a barrier for basing it on strong ETH. And one example of a lower bound that follows from this conjecture is for radius, the radius of a sparse graph. Yeah, for other kind of problems like max flow, maximum matching, very different conjectures might be needed.
Okay, so it seems like you believe that max flow is not in linear time. I'm wondering why, or I mean.
Yeah. Okay, maybe a better candidate would be linear programming or maybe maximum matching on general graphs. Yeah, it's just until we find a linear time algorithm, we should be thinking about a lower bound.
Any other questions? So let's thank Amir again.